Hello class 12. In the last video we learned about power of accommodation of the eye, visual angle, what visual angle is, okay? And we also learned about magnifying power of optical instruments. We saw that the magnifying power of optical instruments denoted by M is equal to the ratio of the visual angle subtended by the image to the visual angle subtended by the object. And basically we place the object when the object is placed at the least distance of distinct vision, as you can see over here. Alright, so keeping these things in mind, we are going to learn about the magnifying power of something called a simple microscope. Now what is a simple microscope? A simple microscope is nothing but a magnifying glass which is in turn a convex lens. So a magnifying glass is basically a convex lens. Simple microscope is basically a convex lens. Now what do we use microscopes for? We use microscopes to magnify the image of very small objects. So we have an object over here, a small object, and we can get to see a magnified image of this small object. So a simple microscope or any microscope basically magnifies the picture, the image of a very small object. Okay, now for this is a virtual image you can see. Okay, the image that we see using a microscope is a virtual image. Now what we do in case of a simple microscope is we basically place the object in between the optical center and focus of the lens. Obviously for a convex lens to form a virtual image, the object has to be placed in between the optical center and the focus. So when we do that, we get to see a virtual image of this object AB, and the virtual image is A dash B dash. Okay, now we assume that this image is formed, the position actually of the object in between the optical center and the focus is so adjusted that the image A dash B dash is formed at the least distance of distinct vision, capital D, from the eye. So you can see D is the least distance of distinct vision between the eye, of course, and the image. Okay, and one more consideration, we are assuming that this eye is very, very close to the lens, such that the least distance of distinct vision, D, this distance, measured from the eye is the same as the distance measured from the lens, that of the image. So what I'm trying to say is the distance of the image from the eye is D. Now since the eye and the lens, they are very close to each other, so the distance between the image and the lens is also D. That is the only thing that I'm trying to tell you. Now, when the object AB is placed at the least distance of distinct vision, capital D, from the eye, then the visual angle that it subtends at the eye is alpha. So for a simple microscope, the magnifying power is beta divided by alpha. Beta is the angle subtended by the image at the lens. You can see beta is this angle. Okay, but since the eye is very close to the lens, so therefore beta is also the image subtended by the eye, image subtended by the image at the eye, remember. Okay, so keeping all those things in mind, so we have beta is the angle subtended by the image A dash B dash at the lens or at the eye, mind you, and alpha is the angle subtended by the object AB at the eye. I have written at the lens over here, okay, but it is at the eye, remember, when placed at least distance of distinct vision. So therefore magnifying power of the simple microscope M is the ratio of angle subtended by the image at the eye to the angle subtended by the object when placed at D. So this is beta by alpha. We've already seen that. Now it's only simple mathematics that we need to check. So since the object AB is very small, the object AB itself is very small, whose image we are trying to magnify. So therefore the angles alpha and beta will also be small. So since AB itself is very small, so this alpha, angle alpha, visual angle alpha subtended by the object at the eye, and this angle, also this angle beta, which is the angle subtended by the image at the eye. Since AB itself is small, so alpha and beta will be small. So therefore, instead of alpha and beta, we can write, tan beta. Okay, so this is equal to AB by OA. Now when we check what is tan beta, where we look at this right angled triangle ABO, so tan beta will be what? Tan beta will be perpendicular by base, so AB divided by AO. And likewise, what is tan alpha? Tan alpha, instead of alpha we can write tan alpha. So tan alpha is AB divided by A, what do I call this? Or rather, simply let me say D. AB divided by D. The base is D. Now, if you want to know why, beta is tan beta and why alpha is tan alpha, for very small values of alpha and beta, okay, you can ask me, okay, I will let you know. But I will not tell that in this video, okay, since I want to shorten this video up. So beta is tan beta, which is AB by OA, and alpha is tan alpha, which is AB by D. So the magnifying power will be this thing, beta divided by alpha, which is this, which is equal to AB, they divide each other out. So this is equal to the least distance of distinct vision divided by OA. Now, what is OA? OA, as you can see in this picture, is the distance of the object from the lens, or I can also say distance of the object from the eye, since these two are very close to each other. Okay. So anyway, AO is the object distance, and object distance, we generally represent object distance by a U. So therefore, the magnifying power M of the simple microscope is capital D divided by U. So you can see I have written over here. So magnifying power of the simple microscope M is capital D divided by U. So this is the expression for the magnifying power of a simple microscope. Many a times I have seen this question come, that is to derive this expression for the magnifying power of a simple microscope. But we can derive other expressions also. This same expression can be extended to other forms. So those different forms are also asked in the exams. We'll try to derive those expressions also. Now we will see this picture again. We'll come back to this picture again. Okay. Now from this picture, AB is on the left hand side of the lens. So the object distance U, is negative minus U using sign convention. Likewise, the image distance V, the image distance, that is the distance of the image from the lens, we denote it by V. Now V is also on the negative side, that is on the left hand side of the lens. So V is minus V, or rather minus D. Since we've assumed the eye and the lens to be very close to each other, so D is the distance of the image from the lens also, mind you. So instead of V, we can write minus D, and instead of U, we can write minus U. So using lens formula, which is this, we get, substituting these values in the lens formula, we get 1 by minus D minus F 1 by minus U is equal to 1 by F. So rearranging here and there, and then multiplying both the sides by D, multiplying both sides of this equation by D, we get D by U is 1 plus D by F. Now, the very first expression that we derive for the magnifying power is M, which is D by U. I have called it equation number 1, as you can see over here. So M is D by U. This is equation number 1. So substituting the value of D by U from this expression in equation 1, which is this, we get M is 1 plus D by F. So this is a second expression for the magnifying power of a lens. Many a times you also get to derive this expression for magnifying power of a simple microscope. Alright, now from this expression you can see that shorter is the focal length, lesser is the value of F, more is the value of the magnifying power. So shorter the focal length, more the magnifying power. Okay. So the magnifying power of a convex lens having focal length 10 centimeters is more than the magnifying power of a convex lens having focal length 20 centimeters, so to say, mind you. Thicker the convex lens, more is its magnifying power, or shorter its focal length. Okay. Also, Now what happens is, so far we had considered the eye to be very, very close to the lens. Now say if this eye is at a certain distance d away from the lens. There is a distance d between the lens and the eye. So in that case, what happens? In that case, the image distance v, that is image distance v, is actually this distance, the distance of the image from the lens. So what will v be equal to? V will be capital D minus small d. Okay, and incorporating sign convention, v will be minus d by d. And therefore the magnifying power becomes, instead of d, we are to write d minus d. So m is 1 plus d minus small d by f. So therefore you can see, the farther away we place the eye from the lens, the greater the distance between the eye and the lens, so to say, the lesser the magnifying power of the simple microscope. Okay, so the magnifying power is reduced if greater the distance between the eye and the lens. So to increase the magnifying power, that is to obtain maximum magnifying power, the eye should be very, very close to the lens. Remember that. Okay, now so far we had assumed the image to be formed at the least distance of distinct vision. So this expression, this expression for magnifying power, also this expression for magnifying power, were for the case when the image was formed at least distance of distinct vision. Now this is a special case, mind you. All right. Now what happens? There is another case that we need to discuss, that is when the image is formed at infinity. So far the image was formed at the least distance of distinct vision. Now what happens if the image is formed at infinity, in which case the eye is in the most relaxed state? So to see with relaxed eye, the image must be formed at infinity, of course. Now when does a convex lens form an image at infinity? A convex lens forms image at infinity when the object is placed at the focus. So when the object is placed at the principal focus, the image is formed at infinity. So in that case, what happens is the object distance is the focal length of the lens. Thereby, from equation number 1 is the first expression for magnifying power, d by u, mind you. So u is f. So when the image is formed at infinity, the magnifying power, the expression for the magnifying power is d by f. So this is for the case when the image is formed at infinity. Sometimes you also get asked this question, remember. The expression for magnifying power when the image is formed at infinity. Okay. All right. So if you're asked that question, mind you, you don't have to go into all these. You don't have to derive this expression. Okay. You will have to derive this, and then simply you'll have to derive this, and then simply you have to write further relaxed eye. That is when the image is formed at infinity. You straight away jump to this, remember. So this is all for the video. Thank you all so much.